In this tutorial, I am going to explain to you two sample problems on image formation by concave and convex mirrors. Before we start, let me just bring your attention to this summary of sign conventions for spherical mirrors. Um, there are sign conventions specifically for a concave mirror or a convex mirror. So it has been agreed that if the mirror is a concave mirror, then we will assign a positive focal length, while if the mirror is convex, okay, we will be assigning a negative focal length. Okay, twice the focal length is also called the radius of the spherical mirror. So it also follows that for concave mirror, the radius must also be considered positive, and for convex, the radius should also be considered as negative. Okay, now for the object distance, we call it DO. If the object is in front of the mirror, then the sign for DO must be positive, while if the object is behind the mirror, this is given a negative DO. For image distance, it's going to be positive if the image is formed in front of the mirror, and we call that a real image. Okay? When it is negative, if DI is negative, then the image is formed behind the mirror, where we have what we call a virtual image. Virtual means unreal. Now, for the magnification, small letter m, if the sign is positive, we can conclude that the image is erect or upright. But if m is negative, we say that the image is inverted upside down. Now, how can we tell that the image is smaller in size compared to the object if the absolute value of the computed magnification is less than 1? We say that the image is reduced in size. If the absolute value of m is greater than 1, then we have an enlarged image. And of course, if the absolute value of m is equal to 1, then the image has the same size as the object. The first problem: a concave spherical mirror has a focal length of 20 centimeters. An object is placed 30 centimeters in front of the mirror on the mirror's axis. Where is the image located? And letter B, what is the magnification the image? Letter C, is the image real or virtual? And the last question, is it erect or inverted? Okay, so we will identify first the given data. We have the focal length of the mirror. Okay, it is positive 20 centimeters. Positive because it is a concave mirror. Then we are also given the location of the object, how far it is from the vertex of the mirror. So we have there this O, meaning the object distance is equal to 30 centimeters. then we are required to find the following. Okay, the image distance denoted here by di. Uh, we also have the magnification. Okay, the magnification, which means how many times is the image larger or smaller than the real object. And likewise, we are to describe the nature of the image, whether it is real or virtual. And the last is for us to determine if the image is either erect or inverted. So to solve this problem, we will first show how to illustrate the given situation using what we call a ray diagram. All right. So already given here, okay, this symbol represents a concave mirror. So it doesn't exactly show you the exact size, but uh, we, we just want to emphasize that the mirror is a concave mirror. Okay, the reflecting surface is facing to the left side. In other words, uh, the rays of light coming from the object will be coming from the left side going towards the mirror, and we have what we call the principal axis. Okay, this horizontal line drawn, okay, is what we call the principal axis. Now, somewhere at this point, okay, you see here a small dot that represents the focus, and the length from the focus to the mirror or to the vertex of the mirror is what we call the focal length. And it is given that the focal length is 20 centimeters. Now, twice the focal length is what we call the radius of the circle. Okay, that is denoted here by capital C. Capital P stands for the principal axis. Okay, so for simplicity, we also draw a vertical line that touches, okay, the point in the mirror known as the vertex. And also, we were told that the object is located 30 centimeters in front of the mirror. So, again for simplicity, we represent the real object in terms of this red arrow. Alright? Notice how the red arrow is drawn. Okay, the tail of the arrow exactly touches the principal axis. And we are here to determine uh, the image, the location of the image of the tip of the arrow. Alright? The tip of the arrow, okay, is a point. And we would like to determine by ray tracing method where that point, okay, is going to be formed by the concave mirror. Now, the reason why we make we may we have the tail of the arrow exactly touching the principal axis, and it doesn't go beyond or downward, so as to assure us that there is no need to determine where the image of the tail of the arrow is. Okay, it can be shown that uh, the image of the tail of the arrow, okay, will just be located within the principal axis. So in other words, as long as we can determine the location of the image of the tip of the arrow, we can already make a deduction as to where the tail of the image of the arrow would be. All right? So, um, the technique of what we call ray tracing diagram is to have at least two incident rays, okay, two incident rays coming from the tip of the arrow, since it is the tip of the arrow that we would like to uh, find out where it's going to be formed, okay, uh, when the ray is reflected from the mirror. All right, we need two incident rays, we call it. All right, now there can be several incident rays coming from the tip of the arrow that will strike the surface of the mirror, but uh, we only choose two incident rays that are considered most convenient. And the first one is, all right, the first one is an incident ray that is parallel to the principal axis. So, as you can see, uh, the light ray comes from the tip of the arrow and strikes the mirror. Okay? What's going to happen if this light ray will be reflected by the concave mirror? All right. We have a rule. Okay, we have a rule that for incident rays or incoming incident rays that are parallel to the principal axis, when reflected by a concave mirror, okay, that ray is going to pass through the focus, something like this. Okay, so we have one. Okay, we have identified one incident ray. Let me repeat. An incident ray that is parallel to the principal axis, all right, when reflected by the mirror, will the reflected ray will pass through the focus. Now, let's have another ray coming from the tip of the arrow. This time we will choose the one that passes through the focus, right? So, another rule in ray tracing diagram, when an incident ray coming from the object passes through the focus, it's going to be reflected by the concave mirror such that the reflected ray will just be parallel to the principal axis. Something like this. Okay? So the blue incident ray is passing through the focus. Okay? When it hits the mirror, it will be reflected in such a way that the reflected ray becomes parallel to the principal axis. So, we also draw the reflected ray. Okay, notice that the two reflected rays, all right, the red one and the blue one, intersect at this point. You see the cursor? That is the point of intersection of the two reflected rays. And what does that represent? This point where the two reflected rays intersect or meet, okay, is now or represents the image of the tip of the arrow, right? So if that is the tip of the arrow, and I mentioned earlier that, okay, the tail of the arrow or the image of the tail of the arrow will just be lying along the principal axis, okay? The image of the object will not be somehow be distorted, so it's going to be uh, pointing along the vertical, but this time, look what's going to happen, okay, to the way the image appears, right? So that arrow, which is pointing downwards, represents the image. of the object, okay, the image formed by the concave mirror. So our task, okay, is going, we are going to determine the distance of this image, how far it is from the mirror. Okay, we call that the image distance. And we are not going to do it graphically because that's going to uh, consume a lot of time, and the objective of this tutorial is really to calculate, okay, calculate the image distance using what we call the mirror formula. All right, how are we going to execute our solution? So the mirror formula, okay, goes something like this. The reciprocal of the focal length, or 1 over f, is just equal to the reciprocal of the object distance plus the reciprocal of the image distance. In short, 1 over f is equal to 1 over dO plus 1 over di. Okay? So we will substitute the given quantities. But before that, let us first isolate di, since that is what we are going to calculate for. All right? So we just transpose 1 over di to the left side of the equation. All right? Before we substitute. And here are the quantities given. The focal length, okay, is 20. For simplicity again, we do away with the given units first. Anyway, all the units here for this, for image distance and for the focal length, the object distance, are all in centimeters. So we know that we are expecting our image distance to be expressed in image or in centimeters. All right, so let's continue now. 1 over 20, that is the reciprocal of the focal length, minus 1 over dO, which is 30. Okay, and simplifying now to solve for di, okay, uh, those who may be wondering how we got 600 here, well, we just determined the least common denominator, okay, in adding fractions, okay, that's usually the method, okay. So our least common denominator, in fact, is 600 di. So if you're going to multiply 600 di to 1 over di, it will just give us 600, no, on this left side of the equation. And 600 di divided by 20 will give us 30 di. All right? Minus 600 di divided by 30 gives us 20 di. And 30 di minus 20 di, of course, gives us 10 di. And now we are able to calculate for the value of the image distance, which is positive 60 centimeters. All right? So that is the distance of the image. It is 60 centimeters away from the mirror. Okay, positive because all computed values, okay, in front of the mirror are considered positive. All right, so we label it in our diagram, and we therefore finally answer the question, the first question, or letter A question, that the image is 60 centimeters in front of the mirror. Okay, moving on with our computation, answering letter B, okay, to determine the magnification of the image. Okay, we have here back to the diagram. As you can see, okay, we just determined the location of the image, and we said that the image is located 60 centimeters in front of the mirror. So we label it here as DI. That's positive. Okay, our image distance is positive. We are given the object distance, which is 30 centimeters. For determining the magnification, we have again another formula. All right. Magnification is denoted by small letter m. Okay, and it is equal to the negative of the ratio of di over do. Okay, so before the parentheses, okay, there is a negative sign. All right, we call this the lateral magnification of the image. Uh, as you can see, it's like we are determining the ratio of the image distance to the object distance. So it's like representing how many times is the image distance, okay, how many times it is larger or smaller than the object distance. Okay, so the magnification, in short, will give you an idea as to the relative size of the image. Okay, so let's substitute our given quantities where we have 60 as our computed image distance, okay, divided by the object distance, 30 centimeters that was given. And then don't forget that there is a negative sign outside the parentheses. So 60 over 30 is 2. That means our magnification is negative 2. All right. What does a negative 2m imply about the image? Right. So first, let's describe the nature of the image. When you say nature, we're just describing whether the image is real or virtual. All right. Another word for virtual is unreal. So how do we know if the image is real or virtual? Okay. The clue is if the DI computed, okay, the image distance, computed image distance comes out to be positive, all right, then we conclude that the object, that the image of the object is real, meaning it is formed in front of the mirror, all right? And since what we got was positive 60 centimeters, therefore, we conclude that the image is real. So, how about the orientation? The orientation is based, okay, on the computed value of m. The sign of the magnification, whether positive, all right, or negative. So since what we got is negative 2, okay, negative 2, which suggests that the image form is in fact inverted upside down, and that is supported by our ray tracing diagram. As you can see in our diagram, if the object is pointing upward, we normally say that it is an erect object, okay, or an upright object. So that's how we describe an object like an arrow here pointing upward. It is upright or erect. And compare the image, okay, that we got. The image is pointing downward, which means that it is inverted upside down. So, in describing the orientation of the image form, we always base it on what we have for the object. So relatively speaking, the image is inverted upside down because our original real object is pointing upward. It's a real object, but the image is a real image as well, but it is inverted upside down. And that is because our computed M is negative. Before I proceed to the second example, there is something about the previous problem that I was not able to emphasize, and I'm referring to the magnification that we just computed, right? So we got a value for m which is equal to -2. Okay, now how will you be able to tell if the image form is bigger or smaller or of the same size as the object? Okay, so as you can see, the absolute value of the magnification, okay, is 2. All right, absolute value meaning disregarding the sign, which is negative in this case. If we disregard the sign of our magnification, we have a value 2. And what does that mean? It gives you of uh, the ratio of the image distance to that of the object distance. In other words, it tells you that, okay, the image, in fact, is twice as large as the object. And that is also supported by our diagram. As you can see, the image form is bigger than the object. Okay, so in terms of magnification, we base it from the value of the absolute value of the magnification. Our second example, we have a convex spherical mirror with a focal length of -20 centimeters. An object is placed 30 centimeters in front of the mirror on the mirror's axis. Letter A, where is the image located? Letter B, what is the magnification of the image? Letter C, is the image real or virtual? Letter D, is the image erect or inverted? Okay, so identifying the given data, we have the focal length, which is -20 centimeters. It's negative because we are talking about convex mirror. Now the object is located 30 centimeters in front of the mirror, so it is a positive object distance. And we are required to find, of course, the image distance and the magnification. Okay, we will also be determining whether the image is real or virtual and whether the image is erect or inverted. Just like in our first example, we have here the ray diagram, and as shown, okay, we represent the convex mirror with this symbol. Okay, we again assume that the incident rays will be coming from the left side and will be striking the reflecting side of the mirror from left to right. So for simplicity again, uh, we assume that the vertex of the mirror is large enough, and this is represented by the vertical line. So again, you have there the principal axis, okay, as well as the focus and the focal length of the convex mirror, which is given -20 centimeters. All right. So you will notice that the focal length or the focus is drawn uh, on this side of the mirror. All right. So others usually refer it to a virtual focus. All right. Now, where is the object located? It was stated that the object is also located 30 centimeters, all right, from the vertex of the mirror. So there it is. Okay. And just like in our ray tracing technique, what we do is to draw an incident ray coming from the tip of the arrow. By the way, the arrow, the red arrow that you see represents the object. Okay. So when we draw a ray that is parallel to the principal axis, okay, this time around, since this is a convex mirror, what will happen to the ray when it strikes the convex mirror? All right. Okay, this is how the reflected ray will behave. All right. So it's going to reflect in that direction. All right. In short, we have a diverging reflected ray, and if we extend this reflected ray backward behind the mirror, okay, it appears to come from the focus. All right, we'll have that again. Right, so there you are. The broken line represents um, the reflected ray, okay, that seems to come from or that appears to emanate from the focus. Okay, so that is represented here by the broken line. This broken line is not actually a representation of the reflected ray. Hence, it is drawn using this broken line. Okay, so it's not a solid arrow because it is not real. So, just like in the first example, again we have to have another incident ray. Okay, from the tip of the arrow, okay, we have another ray. This time the ray is aiming at the focus, right? That arrow there is aimed towards the focus, okay? But exactly at this point, the vertex, what's going to happen to the ray when reflected, right? So what happens is it will be reflected in such a manner that the reflected ray is parallel to the principal axis. When extended backward, okay, using again a broken line that is representing, okay, as if the reflected ray is emanating from this direction, and you will notice that the two reflected rays, okay, the brown ray and the blue ray, has a point of intersection, okay, somewhere here, and that exactly locates the image, okay, the image of the object formed by the convex mirror. And so we represent that with this, uh, again, a broken arrow. The meaning of the broken arrow is that the image is not real. Okay, it is in fact virtual. All right. So, how far is it from the vertex of the mirror? Obviously, it appears behind the mirror, right? So that is again another way of describing that the image indeed is virtual because it is formed behind the mirror, okay, not in front but behind the mirror. So how do we proceed in determining uh, the image distance of this um, image. All right, so this is what we do again using the mirror equation. 1 over f is equal to 1 over do plus 1 over di, and isolating for di, okay, uh, and substituting for the given values, we have negative 20 centimeters for the focal length there, and 30 centimeters for the object distance. Okay, in solving for di, these terms are expressed in fractions. So again, we get the least common denominator, and this is how we proceed. All right, we have negative 600 centimeters on the left side of the equation, and if we multiply this to the least common denominator, actually is negative 600 di. Okay, so when multiplied to 1 over negative 20, what we get is 30 di. Similarly, when negative 600 di is multiplied to 1 over 30, we get a positive 20 di. And 30 di, of course, plus 20 di is, what is that? 50 di. So, okay, simplifying further, we will get the value of di, which is negative 12 centimeters. So that is the distance of the image from the vertex of the mirror. The negative sign of the di, again, uh, confirms, all right, our earlier interpretation that the image is really formed behind the mirror. So it is said to be virtual, right? The image is 12 centimeters behind the mirror. Okay, so completing our computations, we have the magnification where the formula is negative quantity di over do, and substituting, this is what we get. Negative of negative 12 over 30, we get positive 0.4. What does that mean? Alright, positive 0.4 can be interpreted to mean that the image is reduced in size because the absolute value of our magnification is less than 1. Okay, 0.4 is less than 1. So that is what indicates that the image is reduced in size, meaning that the image is smaller than the object. Also, the image is virtual, okay, because once again, the computed di is negative, or that is behind the mirror, and that's why we say that the image is virtual. All right. For the orientation, we base it on the sign of our computed magnification, which is a positive magnification, and we therefore conclude that the image is erect or upright, and that is shown also in our ray diagram. As you can see here, the image, the head of the arrow that represents the image is pointing upward, similar to the original real object. Okay, it is not, the image is not inverted upside down, but it remains pointing upward, vertically up, and hence it is considered an erect image. Before I end my tutorial, let me just share to you a summary of the different cases. There are 6 cases actually of determining the image distance, the nature, orientation, and the relative size of the image. All right. 6 cases for concave mirror and just one case for convex mirror. They are summarized in these table. For example, all right, what we did in example number 1 earlier was case number 3, in which case the object was placed, okay, at a point that is greater than the focal length but less than twice the focal length. So that this was the situation that we described in example number 1 earlier. So when we did the ray tracing together with the computational method, we found out that the image was located at a point twice the focal length. Okay, and what we got was a real image, inverted, and an enlarged image. Okay, that was illustrated in example number 1. So there are other cases 1, 2, 4, 5, and 6. Okay, um, if you're going to analyze problems involving image formation by concave mirrors, this is a very good guide for you to determine the nature, orientation, or relative size of the image. Okay. For convex mirror, it says here that there's only one particular case. Okay. If the object is located in front of a convex mirror, okay, the image form will always be behind the mirror. In other words, it will always be a virtual image, and it's going to be erect, and it's going to be a reduced image. So that's all that we have for convex mirror. There's only one case, unlike concave mirror where there are 6 cases. But out of the 6 cases, there are 2 cases when um, there will be no distinct image form. And this is case 2, if the object is located exactly at the focus or at a distance equal to the focal length. There will be no distinct image. If you are going to prove this using ray tracing diagram, you will find out that the reflected rays will all be parallel to the principal axis, and there will be no intersection or meeting of the reflected rays. Hence, we say that no distinct image form. And there's another case, the last case, case 6, where the object is located at infinity. Example is the sun. The sun's distance from the earth may be considered as infinity. Right? So if you're going to determine the image of the sun, okay, as seen in a concave mirror, you'll find out that it's not going to be very distinct, because the image that is exactly formed at the focus will just appear to be a dot, a very bright spot. All right, and we conclude that the image is not distinct. So thank you very much. That will be all for today's tutorial, and hope to see you in my next video tutorial.